So far, we've studied only normal scaling, in which all segments, no matter where they are, get scaled by the same scaling factor. However, there exist other types of scaling, such as horizontal scaling, in which only the horizontal component of the segments are scaled. This means that if a segment is oriented horizontally, it is scaled normally, but if it's oriented vertically, then it doesn't scale at all. Analogously, we can have vertical scaling, where it's the same, but the directions are swapped. The concepts of horizontal and vertical scaling are going to be really important today, because we're going to talk about areas. And the way we define the area is really dependent on these concepts. Informally, we can define area as the amount of surface an object covers. For example, this object has some amount of area because it covers some part of the surface. And the surface, the thing that is inside of the object, is what we call area. And we need a way to measure that area. The simplest way to measure area is to use squares. So we can say, oh, this square that has side lengths 1 has an area of 1. So we define the area of this square to be 1, and then we measure all other areas with respect to this one. For example, if we want to measure the area of some shape, we can ask ourselves how many of these squares, roughly how many, would cover the surface that this object covers. So maybe like this, and then this part we can distribute right here. And so we can say that this object covers approximately 4 or 5 such squares, so its area should be approximately 4 to 5 squares. But let's start with an easier shape. What about a rectangle that has side length of 1? For example, this rectangle. Let's say this side is 1, and this side is x. What's the area of this rectangle? Well, maybe we can cover it exactly with copies of this square. For example, maybe we can put 3 copies of this square, assuming that this square is the same as this square, is the same as this square, the same as this square, and then we can say that its area is 3, in which case x would be 3. But maybe such division is not possible. Maybe x is 2.73, and then how much would be the area of the rectangle? Here we can apply the concept of horizontal scaling. We're going to scale only in this horizontal direction. Let's take this square and let's kind of stretch it in the horizontal direction twice so that it becomes twice as long. And then we would get something like this. We would get side 1. So this side is vertical, so its length doesn't change during horizontal scaling. But this line here, this segment, is horizontal, and so it changes under horizontal scaling, and now it becomes 2, because the coefficient of scaling, we chose it to be 2. And now we get this rectangle that has an area of 2. And if we had horizontally scaled this so that the coefficient is 3, then we could fit 3 such squares in this rectangle, and then its area would be 3. And similarly, if we horizontally stretched this square by a factor of k, then this length here would be k, and then the area of the rectangle, we can define it to be k. And now because this is the image of this square stretched in the horizontal direction, or scaled in the horizontal direction by a factor of 2.73, then we can define its area to be 2.73. We can apply this property to any other shape. For example, let's take an equilateral triangle. It has some area, S, and then we're going to stretch it horizontally by a factor of, say, 3. Then its base is going to be 3 times as large, and its height is going to stay the same. And because we stretched by a factor of 3, then the area of this triangle is going to be now 3 times S. And yeah, I know, we didn't justify this last thing very well, but as we're going to see in later videos, it's not really hard to prove. Now in the same way, we can apply vertical scaling. Let's apply vertical scaling to this rectangle. Now, if we scale it vertically by a factor, say, of 4, then this new side is going to be 4 times as large, so it would have a length of 4. And then the area of the rectangle, the new area, is going to be 4 times as large as the old area. So the area of this large rectangle is going to be 4 times the area of this small rectangle. And therefore, the whole area is going to be 4 times 2.73. And we can see this by observing how we can fit 4 congruent rectangles, so these 4, that each has an area of 2.73. So the whole thing has an area of 4 times that. And now we can define the area of a rectangle. Suppose we have this rectangle that has side lengths 2 and 3. Then how many of these squares can we fit? Well, obviously 6, which is 2 times 3. So we conjecture that if we have a rectangle with side lengths a and b, then its area is going to be a times b. So first let's take this square and apply a horizontal transformation with coefficient a. We're going to get this rectangle here, which has side lengths 1 and a. And its area is going to be 1 times a, which is a. And then we're going to apply a vertical scaling to this rectangle with coefficient b. And now it's going to turn into our rectangle here because a wouldn't change under vertical scaling and 1 would turn into b. And now this area is going to be the area of the previous rectangle, which is a, times the scaling factor b, which is a times b. So what we did was a composition of horizontal scaling and vertical scaling, resulting in the rectangle that we needed. And you can remember that if we apply normal scaling with coefficient a, then what we're going to get is a square of side length a, and its area is going to be a squared because a is the coefficient of scaling and areas scale quadratically, and so the area would be 1 times the coefficient squared, so a squared. And we can see that the composition of a horizontal and vertical scaling with the same coefficient a both times, so here a and here also a, would give the same square. And its area would be again a times a, so this time we have two a's, which is a squared. The optional problem is to just find the area of this right-angled triangle. It has side lengths a and b. And here is the solution. We just need to construct another right-angled triangle that is congruent to the one given. So we have a right angle here, and then the side b and side a here. If this angle is alpha, then because of the congruence, we have that this angle is also alpha. But now, in the original triangle, we have the sum of the three angles is 180 degrees. So this angle here is 90 degrees minus alpha. So we got a right angle right there. So we got a rectangle. And as we studied, this rectangle has an area S of A times B. But now, because of the congruence, the two congruent triangles have the same area. Let's call it A. So this one has an area A and this one has an area A. And A plus A is the area of the rectangle, which is S. So A plus A equals S, or A equals S divided by 2, which is A times B divided by 2. So if we have a right-angled triangle with sides A and B, its area is A times B over 2.